Hello everyone. We're going to continue with 7.2 on covalent bonding, and I'm going to talk now about these learning objectives. Describe the formation of covalent bonds, and define electronegativity and assess the polarity of covalent bonds. So we'll talk now in more detail about the process by which covalent bonds occur. Again, covalent bonds are formed by the sharing of electrons. So this graphic, I think, helps with that understanding. So if you imagine having an atom of each of the molecules involved in a covalent bond, and you start out with those atoms separated from each other, and as you start moving them closer and closer together, we see a drop in the energy. So the energy is going down. Energy going down means more stable. And that drop in energy is because the nucleus of one atom is attracted to the electrons of the other atom. So as those electrons get closer to the nucleus of the other atom, they become a little bit more stable. And so we have this drop in energy related to that. Now, in terms of the graph itself, don't worry about the specific numbers here. So this is for one particular bond. It will be different for other things. So the distance and the specific energy don't matter too much, other than just understand that when we say zero energy, that's an arbitrary point that we're deciding on, where you have the elements or the atoms by themselves, as we're showing here, by themselves are defined as zero energy, and then when they're in a bond, they have a lower energy than that because they are more stable. And then as we move in this direction, you'll notice that the energy goes up very, very quickly. So these are unstable things, and what's happening here is the nuclei start repelling each other. So that's what's happening in this region. So we have this region in here, and this is the lowest point, but this is where kind of the bond length hangs out in this region. So you will have a similar graph for any set of atoms as you kind of move them apart and move them closer together. There's a minimum location at which the bond forms, and that's what we call the bond length for a covalent bond. Again, for this kind of graphic, it's not going to be about doing any sort of calculation, but just understand what it means in terms of bond lengths. Here we're showing a little bit about breaking chemical bonds. One thing I want to emphasize here, so don't worry about the numbers or doing calculations here, but just the general trend, and we can get that from looking at these equations or from looking at what we're showing here. So going from a bond down here to up here is always endothermic. It always requires energy to break a chemical bond. Okay, always endothermic. Going from having no bond to having a bond is always exothermic. So you're always releasing energy. When you form a bond, you're always requiring energy when you break a bond. We're looking here at a single bond, and the reason I want to emphasize this is that in some situations you might be looking at one bond, but there's other bonds going on in the background that you kind of lose track of. So just know that this is always the way it is, and sometimes it's presented a little bit differently in a biology class because you're focusing on other things. But just remember that breaking a bond is always going to require energy. Forming a bond is always going to release energy. Okay, so let's talk a little bit more about the types of bonds that can happen. We can have sharing of electrons, but it turns out that they are not always going to be sharing exactly equally, kind of like when you share anything, unfortunately. Um, there are a few cases where there is what we call a pure covalent bond, where we have absolutely equal sharing. That is usually going to happen when we have these diatomic molecules, where each of the atoms is identical. So if you have two chlorines, for example, to form Cl2, they're the same thing. They're going to be sharing equally. So that would form what we call a pure covalent bond. When we have an unequal sharing, we call that a polar covalent bond. So this happens when we have different types of atoms present. So HCl would be an example. We have a hydrogen atom and a chlorine atom. They have differences in how greatly they want to have the electron that is shared between them. So how we indicate that is we're showing a few ways we can indicate that down here. If we want to draw a picture, we can show it as in this figure A, where we have kind of a higher coloration for where the electrons are most likely to be, and a lesser coloration where they are less likely to be. And when we say the electrons, we're talking about the electrons that are shared between these atoms, not the core electrons. So the shared electrons are kind of in more towards the greener areas, less towards the wider areas. And we'll look in more detail at this particular type of sharing a bit later. Another way of showing that is what we're showing here. This is called a vector. You may have heard the word vector in possibly a biology class or possibly a math class. And a vector is indicating sort of a direction along with a difference. So a difference in this case is the difference in where we have electron density. And we're saying we have more electron density towards the chlorine. So we have the arrow pointing in that direction. We have less electron density towards the hydrogen. And this is forming kind of a positive sign because when we have less electron density, we're getting kind of like a positive charge. We're getting in that direction. So then the third way we can do this is what we're showing here. So here we're using the Greek letter delta, and I know we've talked about delta before as a triangle. This is the lowercase delta. And so the lowercase delta looks kind of like this. It's often described as looking kind of like a musical note. Not exactly. Actually, the ones we're showing down here are kind of a better written form of the lowercase delta. I'm not going to grade you on how well you draw the delta, as long as it's clear that that's what you mean. And the delta is indicating a partial charge. So it is not a full positive charge. It is not a full negative charge. You can think of it as something between 0 and +1 or 0 and -1. So the result of having this unequal sharing is that you're starting to get more like an ionic compound. And so we're indicating that in this way with the partial positive and partial negative charges. So the reason why a bond might be polar or nonpolar is related to a property called electronegativity. Now, of course, we know if the atoms are identical, it will be purely covalent, but different elements have different properties in terms of their ability to attract electrons within a shared chemical bond. And so we measure that with something called electronegativity. When you have a polar covalent bond, the electrons are more towards one of the atoms than the other, whereas when you have a nonpolar covalent bond, the electrons are more shared equally between the atoms in the bond. We're showing here basically a periodic table that is showing electronegativity trends. And you don't have to memorize these numbers. You will be doing some calculations related to these numbers, but you would want to basically do two things. First of all, if you are provided this information, can you perform those calculations? And then secondly, if you are not provided this information, can you say what the trend is? And that is without memorizing the numbers, but just what is the trend? And the trend is that we increase electronegativity as we move towards the right of the periodic table, so towards the non-metal side. And we decrease electronegativity as we move down the table, so from top to bottom. And so the most electronegative element is, because we're leaving out the noble gases, you'll notice, is fluorine. The noble gases can sometimes form chemical bonds, but they are not included in this table. So we will omit them for now. So fluorine is the most electronegative. It is whenever you have a bond with fluorine, the sharing of electrons is mainly going to be on the fluorine side of things, as opposed to more equal sharing. And then as you move away from fluorine, so as you move down and to the left, that amount gets lesser. Again, you don't need to memorize these numbers, but do understand the general trend in terms of where it is the highest and where it is the lowest, and also be able to do some calculations with these, as we'll see here in a moment. Just to point out, this is not exactly the same as electron affinity, because electron affinity is something that can be measured by experimentation. This is a calculation that is done based on observed things, as opposed to just a experimental result. So just be aware of that difference as well. So there is a relationship between electronegativity and the type of bond. And what we're looking at here is the difference in electronegativity of the bonded atoms. So there are some possibilities here. If there is zero difference between the electronegativities of the bonding atoms, we would say we have a pure covalent compound, or pure covalent bond. There's nothing at all polar about it. If there is a large difference, we would say we have an ionic bond, because we have a complete transfer of electrons. And between those two extremes, we would say we have intermediate. We would have a polar covalent bond. In general, we can see which range we would fall into here. So generally, if the difference between electronegativities is less than 0.4, we would say we have a pure covalent bond. If it's greater than 1.8, we would say we have an ionic bond. And if it's between those two, we would have a polar covalent bond. I am not going to expect you to memorize these numbers. This is something where if you are provided with this information, you would also be provided with this information, and then from that you would make your decision. So this is kind of a rough approximation, but it works in many situations. So there's some examples here of calculations related to that and how you would make the decision on polar or non-polar bonds. So that is it for section 7.2.